Welcome to our deep dive today. We're going to be exploring this fascinating world of robust machine learning, specifically in the context of distributed systems.
Okay.
We'll be using excerpts from Robust Machine Learning. It's a book, a great book actually, called Robust Machine Learning Distributed Methods for Safe AI by Rachid Guerraoui, Nirupam Gupta, and Rafael Pinot. And this is really going to guide our exploration today.
That's good.
So to really kind of set the stage, we're going to be focusing on how to make algorithms, particularly like distributed mini-batch gradient descent,
Right.
resilient to having like Byzantine or malicious nodes in the network.
Yeah, this is a really important topic, especially when we consider that the standard approach to distributed machine learning, like the
Yeah.
kind used in federated learning, often relies on this assumption that all of the nodes are being honest.
Right.
They're going to be contributing valid information.
Right.
But unfortunately, in the real world,
Yeah.
this assumption, it can break down quite easily.
Yeah, absolutely. So how do we even begin to like quantify and address this like vulnerability that you're talking about?
Yeah, so the book introduces a couple of crucial concepts that we're going to be talking about today. One of them is this idea of a breakdown point.
Okay.
And this quantifies really what fraction of malicious nodes that an algorithm can tolerate
Okay.
before it just totally falls apart, breaks down.
Right.
For instance, you can imagine a breakdown point of, let's say, zero point 0.2 or something like that. That would mean that the algorithm that we're talking about can withstand maybe up to 20% of the nodes being malicious before it fails.
Okay.
So that's the breakdown point.
Gotcha. So a higher breakdown point means that it's more robust, I would imagine?
Exactly, exactly. And then another important concept that
Yeah.
we should talk about is this thing called resilience.
Yeah.
And you can kind of think of this as a performance guarantee even when you have these malicious nodes around.
Okay.
So what this is asking is, can we design an algorithm that produces a model that's only a little bit worse, we call it A worse, than the best possible model, even if we have up to F of these nodes that are being bad, what we call Byzantine.
Okay, so it's not complete immunity. It's more like we're just trying to control
Right.
the impact that these nodes can have.
Exactly. We just want to make sure that it's bounded and controlled.
Gotcha.
And the authors of this book delves into a whole bunch of techniques
Yeah.
to try to achieve this resilience.
Okay.
And one of the key things that they talk about are robust aggregation methods.
Okay.
So you can imagine in distributed mini-batch gradient descent,
Right.
each one of these nodes computes its own local gradient based on its own data.
Right.
And then all of these gradients have to get sent to a central server,
Yeah.
which then aggregates them all to update the global model.
Okay.
Now, traditionally, people have just used simple averaging
Yeah.
to do this aggregation step.
Right.
But it turns out that this is really susceptible to manipulation
Yeah.
by these malicious nodes.
Yeah. So that's where these robust aggregation methods come in.
Exactly.
Okay.
Exactly. So the book explores some really nice alternatives to simple averaging,
Okay.
and each one of these alternatives has its own strengths and weaknesses.
Okay.
So one method that they talk about is this thing called coordinate-wise median.
Okay.
So instead of taking the average across all the gradients for each dimension, we compute the median.
And what's the benefit of the median there?
So the median is a lot less sensitive to these extreme values
Okay.
that malicious nodes might try to inject
Oh.
to disrupt the learning process. So even if a couple of nodes some gradients that are totally off,
Yeah.
the median will basically stay unaffected.
It's a pretty clever approach. What are some of the other approaches?
Yeah, so another one is called the geometric median.
Okay.
And this one seeks to find a point that minimizes the total Euclidean distance to all the different vectors that come in. And this method is known to be very robust, especially to outliers.
So instead of looking at it one dimension at a time,
Yeah.
it's more like looking at it holistically in terms of the geometry.
Exactly.
Okay. Interesting.
Yeah.
And are these computationally expensive compared to just averaging?
So these median-based methods, they can be a bit more expensive than averaging. So the book also explores other techniques like, for example, the trimmed mean,
Okay.
which discards, let's say, the top and bottom 10% of the values before averaging. So it's kind of like a compromise.
Right. So you get kind of a mix of
Yeah, compromise.
robustness and efficiency.
Exactly.
Okay. And what else?
And then there's also multi-crumb. This is a bit more intricate. It's a method that tries to select the gradient vector that is closest to its neighbors, in a certain sense. It's a clever way to identify and reject outliers.
So it seems like each of these has their own like pluses and minuses.
Exactly,
Yeah.
exactly. And choosing the right method will depend on the application that you're interested in, what kind of accuracy you're looking for, and how much computational cost you're willing to pay. But robust aggregation is only one part of the story. The book also delves into this idea of pre-aggregation techniques.
Okay.
And these techniques, you apply them to the input vectors before you even do the aggregation step.
Yep.
And that can further enhance resilience.
So you're basically like cleaning the data before.
Exactly. You're pre-processing it to make it harder to manipulate.
Okay.
So one technique like that is called nearest neighbor mixing. We call it NNM for short.
Okay.
And here, each vector is replaced by the average of itself and its, let's say, NF nearest neighbors. Here is the maximum number of Byzantine nodes that we think we might encounter.
So what's the intuition behind that?
Right.
Why is that helpful?
So the intuition is that by mixing each vector with its neighbors,
Yeah.
we're essentially pulling the good nodes closer together.
Okay.
And that makes the malicious nodes stand out more. It's
Okay.
kind of like if you had a store and you group together all the similar items,
Yeah.
it would be easier to spot the ones that don't belong.
Gotcha.
Yeah. And so
And does this affect the accuracy at all?
this mixing, this NNM thing, it gives you what we call deterministic robustness.
Okay.
So it guarantees a certain level of resilience. But, it does come with a cost. You have to compute all these nearest neighbors.
So again, there's a trade-off there.
Exactly.
Yeah.
There's always a trade-off.
What other pre-aggregation techniques are there?
Yeah. So another one is called bucketing.
Hmm.
And in this method, we randomly divide up all the vectors into different buckets.
Okay.
And then we aggregate within each bucket.
Right.
And then finally, we aggregate all the bucket results.
Okay, so it's kind of like a
Right.
divide and conquer type of approach.
Exactly. Exactly.
Okay. And why is that helpful?
Well, the idea is that when you randomly distribute these vectors into buckets,
Yeah.
you're kind of diluting the impact of any Byzantine nodes.
Okay.
Because it's less likely that one single bucket is going to be dominated by these bad actors.
So it's like using randomization to
Adversarial.
increase the robustness.
It's-
Okay. And how does that compare computationally to the
Right. So
yeah, no.
bucketing is more computationally efficient than NNM,
Okay.
but it provides what we call stochastic robustness.
Okay.
So its effectiveness is probabilistic. It might not always be perfect, unlike NNM, which guarantees
Right.
that it will always work.
So again, each one has their own
Yeah.
strengths and weaknesses.
Exactly. And it really depends on the specifics of your problem, what kind of risk you're willing to tolerate.
Right.
The book goes into this really nice theoretical analysis of all these methods.
Yeah.
And it shows that if you combine them in the right way with the right robust aggregation technique, you can actually achieve what we call order optimal training error.
Order optimal meaning.
Meaning it's basically the best that we can hope for, given the fact that there might be these adversaries lurking around.
We're not just making it robust. We're also making sure that it's
Right.
as good as it can be.
Exactly. So
Yeah.
we're not just making it robust.
Right.
We're making sure that it's as accurate as it can possibly be under these difficult conditions.
Gotcha.
Now, the book doesn't stop there. It also explores this concept of momentum
Yeah.
and how that can be incorporated into distributed learning algorithms
Right.
to even further enhance the robustness.
Momentum, like in physics.
Yeah, just like a moving object with a lot of momentum is less affected by like small bumps and irregularities in its path.
Right.
Momentum and optimization algorithms can really help to smooth out this learning process
Yes.
and make it less susceptible to sudden deviations that can be caused by these malicious nodes.
So it's like giving the algorithm some
Yeah.
inertia so that it can't be pushed around as easily.
Exactly. And this brings us to a specific algorithm that they talk about in the book.
Okay.
It's called robust DMHB, which stands for Robust Distributed Me-Batch Heavy Ball.
Robust DMHB.
Okay, and we'll talk more about that next time.
Okay, great.
But that's an algorithm that really incorporates this idea of momentum.
Okay, awesome. So I guess we'll pick it up from there next time. We'll dive into the specifics of robust DMHB
Sounds good.
and its performance guarantees. Until then,
Okay,
keep those mental gears turning.
sounds good.
All right. See you next time.
Okay, bye.
Welcome back to our deep dive into robust machine learning.
Glad to be back. Let's delve a little deeper into this whole concept of distributed momentum,
Sure.
and specifically this algorithm we talked about last time, robust DMHB.
Yeah, robust DMHB. So as we were discussing, it incorporates this momentum at each node to kind of smooth out the updates.
Right.
And make it less susceptible to those sudden disruptive changes that those Byzantine nodes can introduce.
Yeah.
Can you talk a bit more about how this momentum term is actually calculated and how it fits into the whole learning process?
Sure. So in robust DMHB, like we said, each node, instead of just using its current gradient, it keeps track of this thing called a momentum vector.
Okay.
And at each step, this momentum vector is basically a weighted average of the current gradient and the previous momentum vector.
Yes.
And this weighting is controlled by a parameter that we usually call beta.
So a higher beta means that we're giving more weight to the history of the gradients.
Exactly. So that'll make the update smoother, but it might make it converge a bit slower.
Right. Okay. So there's there's a trade-off.
Trade-off there.
Yeah. And tuning that beta parameter is super important to get good performance.
Yeah.
Now, remember, we're in this distributed setting, right? So we eventually have to take all these momentum-updated local models and aggregate them at the server to update the global model.
Okay.
And that's where those robust aggregation methods,
Right.
like the coordinate-wise median or the geometric median, that's where they come in.
So you're basically combining this smoothing effect of the momentum at each node with the robustness of the aggregation at the global level.
Exactly. It's like a double layer of protection.
Oh, okay, gotcha. So that makes the whole system much more resilient than traditional distributed gradient descent. Exactly. And the book goes into this very rigorous theoretical analysis of robust DMHB.
Okay.
And they introduce this concept of F, stationary resilience, to actually quantify its robustness.
Okay, now I remember we talked about FA resilience before.
Yes.
Right, we were talking about the training error.
Yeah.
How is F stationary resilience different?
Good point. So F resilience, like you said, focuses on the final training error of the model.
Right.
But Hef stationary resilience, that focuses on something we call the stationarity gap.
Stationarity gap.
Yeah.
Can you remind me what that is again?
Yeah. So in simple terms, it measures how close the current model parameters are to a point where the gradient of our loss function is 0.
Okay.
So in optimization, especially for these non-convex problems, which are very common in machine learning, these points where the gradient is 0, we call them stationary points.
Okay.
They basically represent locations in this parameter space where the model's performance is kind of stable.
So it's like reaching a stable point.
Exactly. In the learning process.
Yeah, like a stable equilibrium.
Okay.
And stationary resilience basically guarantees that even with up to F of these Byzantine nodes, robust DMHB will converge to a point where that stationarity gap is at most.
Okay.
So in other words, the algorithm is guaranteed to find a pretty stable solution.
Okay.
Even though there might be some bad actors trying to mess things up.
That's really important when you think about applications where even a small deviation from a stable solution could be catastrophic, right?
Absolutely.
Okay. So the book also talks about some theoretical results about how well robust DMHB actually performs.
Yeah. Can you summarize some of the key findings?
Yeah. One of the coolest findings is that robust DMHB actually achieves order optimal training error, even with these Byzantine attacks going on.
So again, it's the best we can hope for.
Exactly.
Given the circumstances.
Given the limitations, yeah.
Okay, that's impressive.
So this shows that the robustness doesn't come at the cost of accuracy, which is a great thing.
Absolutely. But I mean, achieving that accuracy is only one part of the story, right?
Right.
We also need to think about how computationally efficient these algorithms are, especially in a real-world setting where you might have tons of data and all these different nodes.
That's a crucial point. And the book actually highlights that robust DMHB achieves this order optimal training error with what we call a much lower gradient complexity.
Gradient complexity.
Yeah, it's basically a measure of how many gradient computations you need to do throughout the whole training process.
Okay.
So lower gradient complexity means the algorithm is more computationally efficient.
Gotcha. So it's robust, it's accurate, and it's also relatively computationally inexpensive.
Relatively lightweight.
Okay.
Yeah.
That's great.
So, I mean, are there any caveats or specific conditions where these impressive results might not hold true?
That's a good question. Of course, like any algorithm, robust DMHB has its nuances. The book does point out a few things that can influence how well it performs. One of them, as we discussed before, is how you tune that momentum parameter, beta.
Right.
They actually propose a specific way to adjust that parameter over time. which is really important to guarantee that it's going to converge, even with those Byzantine nodes.
So it's not just like a set it and forget it.
Exactly. It's not one size fits all. You might need to do some experimentation and fine-tuning depending on your application.
Okay.
Another thing they emphasize is this level of data heterogeneity across the nodes.
Heterogeneity meaning?
Like how different the data sets are
Right.
on each individual device.
Gotcha.
If the data is very similar across all the nodes, then robust DMHB, it works like a charm.
But if the data is very diverse, meaning different nodes have very different types of data, then it can become harder to achieve that order optimal training error.
So the more diverse the data,
Yeah.
the harder it is to build a system that is truly robust.
It definitely adds to the challenge.
Right.
Yeah.
Okay, now before we wrap up this section, I wanted to revisit the concept of the breakdown point, particularly in the context of these different robust aggregation methods. Right? I know we touched upon it before,
Yeah.
but I think it deserves further exploration.
Absolutely. It's a fundamental concept when you're evaluating robustness, right? Especially when you have these Byzantine adversaries.
Yeah.
It tells us what's the maximum fraction of malicious nodes that an algorithm can tolerate
Okay.
before it just completely collapses.
So it's not just about mitigating the impact, it's
got
also
it.
about understanding the limits
Yeah, knowing your limit.
of what we can tolerate.
Exactly. And what's really interesting is that different robust aggregation methods actually have different breakdown points.
So some are inherently more resilient.
Precisely.
Okay.
For example, those median-based methods we talked about, like the coordinate-wise median and the geometric median,
Yeah.
they tend to have higher breakdown points
Huh?
than methods like trimmed mean.
And why is that?
Well, it's because medians, by their very nature, are less sensitive to those outliers,
Okay.
which is exactly what the Byzantine nodes are trying to inject.
Gotcha.
Yeah. So if you're in a situation where you think you might have a lot of malicious nodes,
Right.
it might be a good idea to choose one of those median-based methods.
Okay.
But of course, there's always a trade-off, right?
Right.
While these median-based methods are more robust in terms of their breakdown point,
Yeah.
they might not always achieve the lowest possible training error
Right.
if all the nodes were actually being honest.
So again, it's all about choosing the right tool for the job.
Exactly. And it really depends on your needs and what you expect the level of adversarial activity to be.
Right.
Yeah.
You got to balance that robustness and the accuracy.
Absolutely. It's a balancing act. And it highlights a key message that the authors want to convey. There is no one-size-fits-all solution
Right.
when it comes to building these robust and trustworthy AI systems.
Okay.
It takes a deep understanding of the algorithms, a good analysis of the data,
Yeah.
and a real awareness of the potential threats.
This has been a great deep dive so far.
Yeah.
I'm really struck by the fact that there's no silver bullet solution here.
No silver bullet. It's all about understanding the nuances
Okay.
and choosing the right approach for your specific situation.
Okay, so let's recap what we've covered so far in this deep dive.
Mhm.
We've talked about a whole bunch of techniques aimed at making distributed machine learning more resilient to these Byzantine attacks.
Yeah.
Right?
Yeah, we've covered a lot.
We talked about robust aggregation methods, pre-aggregation techniques,
Right.
the whole concept of distributed momentum, which led us to this robust DMHB algorithm.
Right.
We talked about these ideas of the breakdown point and stationary resilience.
It's been a whirlwind tour.
So I think in the final part of our deep dive,
Okay.
we can maybe synthesize all these different insights and maybe talk about some broader implications of this research.
Yeah, I think that'd be really interesting. We can explore how this work might impact the future of trustworthy AI.
Okay, great.
Yeah.
Looking forward to it. Until then, keep those mental gears turning.
Absolutely. See you next time.
Welcome back to the final part of our deep dive into robust machine learning.
It's been quite a journey, hasn't it? Exploring all these different ways to make AI more trustworthy.
It really has. We've covered so much ground, from those robust aggregation methods to the pre-aggregation techniques and that whole idea of distributed momentum.
And we really dug deep into the theory behind it all, understanding how these methods can achieve both robustness and accuracy, even when we have those Byzantine adversaries trying to throw a wrench in the works.
As we wrap up this exploration, I think it's important to step back for a moment and think about the bigger picture. What are the broader implications of this research?
That's a great point. As AI becomes more and more integrated into every aspect of our lives, things like healthcare, finance, even things like self-driving cars.
Yeah, critical stuff.
The need for trustworthy AI, it just becomes absolutely paramount.
We need to be able to rely on these systems to make good decisions, even when they're faced with like uncertainty, errors, or even those malicious attacks we've been talking about.
And that's where this research really shines.
Right. By understanding the vulnerabilities in those traditional machine learning algorithms
Yeah.
and developing these new techniques to make them more resilient.
Exactly. We're essentially laying the groundwork for a future where AI is not only powerful, but it's also something we can actually trust.
And it's not just about safety and reliability, right?
Yeah.
There's also the ethical considerations.
Absolutely. Trustworthiness, it's a multifaceted concept. It encompasses things like transparency, accountability, and fairness.
So this isn't just a technical challenge, it's a societal one too.
Couldn't agree more. Building truly trustworthy AI, it's going to require collaboration. We need researchers, engineers, policymakers, even the public, all working together.
One of the things that really struck me throughout this deep dive is that there's no one-size-fits-all solution.
Exactly. It's all about finding the right approach for the specific problem you're tackling, thinking about the data you have, the potential threats, everything.
Right. And having a really solid grasp of those underlying algorithms, what their theoretical guarantees are.
It's an ongoing process, really. Always researching, developing, refining, always striving for better.
Well, this deep dive has definitely given me a lot to think about, that's for sure.
Me too.
I really encourage our listeners to check out the book we've been discussing. Dive into those concepts in more detail. It's a fascinating read.
And I'd add, stay engaged in the conversation. This is an evolving field, and it's one that's going to shape the future in profound ways.
That's a great point. Well, on that note, I think it's time to wrap up this deep dive into the world of robust machine learning.
It's been a pleasure exploring these ideas with you.
Likewise. And to our listeners, thank you for joining us. Keep those minds curious, and we'll see you next time.